118 degrees, right? The value of the central parallel of the zone minus the L of Bernardino, 117 something, 116 something. Yeah, times the sine of B sub O, and gamma ends up equaling, I'm going to need more room than that. If you do the math, I got 0 degrees, 37 minutes, 27 point, there it is, 428, 335. And because we're going to be doing trig functions, you need to take it out as far as you can. My suggestion is when you do the calculation, store it in a register in your calculator. So you store as many decimal places as you can. Okay? It ends up being, now does that make sense? Should it be a positive value? Should gamma be positive in this case, or should it be negative? Is it east or west of the central meridian? We're east, therefore gamma will be positive. If you do the math correctly, gamma will come out negative if you're on this side. Okay, so now we have our, I didn't write it down anywhere, did I? Or did I? I did somewhere. There we go. We have R. We have gamma. Now you can simply put those values into these two formulas here and calculate the northing and the easting of Point Bernardino. And if you do that, you end up getting a northing for Point Bernardino of 1,931,595.238 and an easting of 6,892,450.944. And these are in U.S. survey feet. Now, without even checking my math and see if I did it right, do these numbers make sense? In general, do these numbers make sense? 2 million, 6 million. Okay, they make general sense for California. First thing you do, if you got 64 million for the northing, probably got a math problem. First thing you do is, do the numbers make sense? Then you double check your math. And I think this is right. Okay, so questions so far? Yeah. Questions so far?
L for Bernardino, that was, just had to make sure my diagram's okay.
That should simply be, B is latitude, L is longitude. And so longitude is 116.54 or something, whatever it is.
54.17.
Yeah.
That's your convergence angle right there, that's 0 degrees 27.
Yeah.
Where would that second term come from, and why would it be used?
There is a second term, and that's more applied when we get to determining our azimuth, and we'll talk about that in a minute. We'll talk about when we talk about our azimuth. There's a second term there. There's also you got to be careful of your distance in some cases also, based on how long your distance is. There's a correction to that also. We don't have to do it on this problem, but we'll talk about it. Okay? Let's take a quick 5-minute break, stretch your legs or whatever, and then we'll come back and see if we can finish up by 12:30. Make it fast, please. Hear me? Okay. We're not going to do the actual mathematic calculation from state plane coordinates to geodetic coordinates, but if this is our triangle, and we know the easting and we know the northing of a point, and we know our constants, how would we figure out the latitude and the longitude of Point Bernardino if we had to go that direction? Okay, if we know R sub b and n sub b, and we know the northing, then we know r cosine gamma, right? By doing subtraction, we can figure out what r cosine gamma's value is, correct? If we know E sub O, and we do the easting, we can do a subtraction and get r sine gamma, correct? By simple trigonometry, we can figure out gamma. By Mr. Pythagorean's theorem, we can figure out r, correct? If you know what r is, you can look in your projection tables, and you'll know that that value, that 30 million feet dimension, will be between 2 even minutes, correct? And working back through, you could then figure out what the difference is and figure out what the number of seconds are. Kind of maybe could have. And then working through our gamma, if we know this and this, we know gamma, we can apply that to, we know the longitude of the central parallel, and applying those correctly, you could then figure out what the longitude of Point Bernardino would be. Okay? We're not going to work through it, but you can just work backwards through the equations. Kind of makes sense? In your handout, I think I gave you a step-by-step way of doing that. If you go through the handouts, I gave you some step-by-step procedures to go through and do those things, either using the projection table or using the polynomial coefficients. The next thing we have to work on is we need to determine the azimuth from Bernardino to Riverside. I think I gave you the geodetic value, the geodetic azimuth. So let's draw our triangle again. Apex of the cone up here, and Point Bernardino over here. And this is L sub O down here. And this would end up being gamma, correct? Okay. On this simple little diagram right here, what represents geodetic north? Geodetic north, remember, is based on the sphere. Okay? And as we worked our way through developing our surface, this would end up being geodetic north, correct? Because theoretically, this is a line of longitude. Line of longitudes converge on the North Pole, or for our problem here, they converge at the apex of the cone, correct? So this direction from B to the apex of the cone represents geodetic north. Okay? Does it represent astronomic north? David talked about the Laplace correction. Astronomic north is slightly different. Generally less than 20 seconds. 20 seconds of difference. Well, astronomic to geodetic is extreme. Down in Southern California where I teach, I figured it out. It's like 5 seconds of difference between the two. If they're going to ask you the difference between astronomic and geodetic north, they will tell you the Laplace correction. You don't have to figure that out. And you'll just have to figure out what it is and apply it correctly. Okay, so this represents geodetic north. How about if I have a point over here somewhere? What does this represent? Geodetic north. Geodetic north, as long as it points at the apex of the cone, every line represents geodetic north. The central parallel is geodetic north. Matter of fact, the central parallel is the only line that is both geodetic north and it's grid north, because that's the line we use. How would I represent grid north for point B? Isn't it going to be, we're on a grid system, so isn't it going to be parallel to our central meridian? And if this is gamma, what's that value? That's also going to be our convergence angle, which is gamma. Okay, what's the geodetic? I gave you the, hang on, how did I give it to you in the problem now? Give me a second here. Yeah, hang on. I gave you, there it is. I gave you the angle from the azimuth mark, and I gave you the azimuth, the geodetic azimuth of the angle mark. So how do I draw on here, how do I draw a line that represents the geodetic azimuth from Bernardino to the azimuth mark? Okay, it's going to go something like, this is 0.37, right? I didn't write it down. This is about 30, the gamma's 30, what, 30-something minutes?
37.
And this is 2 degrees. I got to think about this. Riverside's over here somewhere. And so the azimuth mark is actually up this way, correct? And this angle right here is 95/16/46. Okay, so far? And this is the azimuth mark up here. Okay, so how do I put in the azimuth, the geodetic azimuth of 2 degrees, 21 minutes, 33 seconds? How do I show that graphically on here? Well, if this is geodetic north, then this angle right here must be 2 degrees, 2133, yes? If this is geodetic north and the geodetic direction to the azimuth mark is 22133, then that must be this angle here, correct? Okay. How do I show the geodetic azimuth to the line between Bernardino and Riverside? How do I show the geodetic azimuth, graphically show the geodetic azimuth up here for the line between Bernardino and Riverside? Again, if this is geodetic north, then this represents the geodetic azimuth from Bernardino to Riverside, right? So, what is the geodetic azimuth from Bernardino to Riverside?
97, 38, 19.
97, 38, 19. Very good. We know this value here. We know this value here. Therefore, this value here must be, the geodetic azimuth must be 97 degrees, 38, 19. Does that make sense? Remember, we're referencing off of this. This, I can't remember what the symbol is for the geodetic azimuth. Oh, it's alpha. This is alpha in the state plane coordinate world. Alpha is the geodetic azimuth. Okay so far? So how am I going to calculate the grid azimuth from Bernardino to Riverside?
subtract gamma.
Thank you. That's not little t, it's the Greek letter that looks like little t, and I can't remember what it is. Grid azimuth is going to be from grid north to the line between Bernardino and Riverside, right? And based on what we know here, we know geodetic right here. We know geodetic. We know the convergence angle. If I simply subtract those two values, that will give me t, right? Or Greek letter t. So, based on that, the grid azimuth, small t, is going to equal geodetic azimuth alpha minus the convergence angle gamma plus what's called the second term that I think you were asking about before, plus the second term. Let's talk about the second term. First of all, we will end up ignoring the second term on this problem because it doesn't apply, but we'll talk about what it is so you understand. So we will ignore the second term for our calculations, and our grid azimuth is going to end up being from Bernardino to Riverside, if you do the math, 97 degrees, 00 minutes, 51.6 seconds.
I don't remember what the gamma was, so I didn't do that one.
That's right. Gamma is whatever we calculate, 34 minutes or something like that.
37, 27.
Yeah. So our grid azimuth ends up being 97.0056. If I subtract the geodetic azimuth minus our mapping angle, or excuse me, our convergence angle, which was 03727.4, you could do just 42, 43 here. Okay, so far? So we know the grid azimuth between the two, and we're trying to calculate that. So that's what it ends up being. As far as the second term goes, for the second term, remember, we're working on a flat plane now. We're working on a two-dimensional plane. We're working in northings and eastings. I should have just grabbed a whole bunch. So from Bernardino to Riverside, Riverside and Bernardino, this line right here represents our grid azimuth T, straight line on the grid plane. Our geodetic azimuth is based on a sphere, correct? Geodetic azimuth is a spherical direction. What happens when you project a straight line on a sphere to a 2D surface? What happened to our lines of latitude? Our geodetic azimuth is going to be something like this. When you project a straight line from a sphere to a plane, it's the projection's going to create this. This line's going to become curved. Okay? Right here, the angle between the tangent right here at the beginning and our grid is the second term. The angle here between our straight grid line and the tangent of this arc right at this point is the second term. Okay? If this distance is under 2 miles, the second term is negligible. If this distance is under 2 miles, the second term is negligible. In your handout somewhere, I gave you the formulas for calculating the second term. It's a little bit complicated based on either northings and eastings or latitude and longitudes, but you can calculate what that value is. In this case, our distance is under 2 miles, so we'll ignore it. Does that make sense? But on the LS exam, well, again, you guys are working in a different LS exam. If somehow you have to write the formula, even if you don't use it, write down second term in the formula. Okay? Because it is part of the formula. So, we know our grid coordinates for Bernardino. We know our grid azimuth from Bernardino to Riverside. We're 2/3 of the way there. Now all we have to come up with is the grid distance from Bernardino to Riverside. Okay? And in the problem, questions? I should get this, like I said, on PowerPoint. How did I express it in the problem? I'm supposed to know all this. I gave you the distance is a slope distance from Riverside to Bernardino. So what we have then is we have Bernardino up here, and the elevation of Riverside is down here, right? And the distance is 8236, the slope distance, 0.87 feet. And this is at an elevation of 1253.80, and this is at an elevation of 987.99. Did I put 88? I got 99 on my sheet, but okay. So far, so good. Looking at from the side. Oh, I see. Okay, thanks. Okay, so far? What's the definition of a horizontal line? Straight line between 2 points. So this is a horizontal distance?
Perpendicular normal to straight line between 2 points at the same elevation.
So this is the horizontal distance from here to here? For almost all the work you do, yes, but in state plane coordinates, no. The horizontal distance between any 2 points is the distance between the lines, if you will, the distance between the vertical lines running through those 2 points. The horizontal distance between any 2 points is the distance between the vertical lines running between those 2 points. So, the horizontal distance from Bernardino to Riverside at the elevation of Riverside is different than the horizontal distance between Bernardino and Riverside based on the elevation of Bernardino. Used to be called the elevation factor. Okay, this is what's going on. Okay, the horizontal distance will vary depending on the elevation. Now, if you do the math here, and you know this, and you know this, and you solve the right triangle here, I think you end up with a distance of like 82, 32, 577 feet. If you simply solve this right triangle, you end up with this dimension. Where do I put this dimension? This dimension is going to be the dimension halfway between the two. It's going to be the distance, 8232.577, at an elevation of 1120.94 feet. There is a way to calculate it here, there is a way to calculate it here, but we don't have time to go into that today. That's more geodetic surveying. Okay, so the horizontal distance you calculate by solving this right triangle is the average, or the horizontal distance at the average elevation between the 2 points. I don't want to confuse this with this, so that's the elevation. Does that make sense? Okay. So we have our measured distance at a specific elevation. It's actually a two-step process to get to the grid distance. You can do it in one using what's called the combination factor, but I'm going to try to show it to you in two. I think we have enough time. We're going to go to the geodetic distance first. Geodetic distance is what? Is the distance at? Geodetic distance is the distance at sea level. It's the distance along the ellipsoid, or the datum, which is a theoretical sea level. Then we will go from geodetic distance to the grid distance. Okay? You can do it in one step. We'll do it in two. So if I draw this like this, and here we are at an elevation up here, somewhere down here is sea level, or the ellipsoid, or the datum. Let's call it the datum. And the datum is NAD 83, right? Okay. And so what we end up calculating is actually the chord across here, what's called the long chord. So if we've got a distance here at an elevation, and we need to know the distance here at the elevation of the datum, it's just similar triangles. And all we're going to do is come up with a conversion factor that is a similar triangle. The center point's the Earth mass center. And so we're just going to solve this based on similar triangles. Make sense? To do that, based on David's conversation this morning, based on David's conversation this morning, we have the geoid down here, and the ellipsoid or the datum is above that. Remember he was talking about that in North America? This dimension right here, I'm going to kill myself up here. This dimension right here is what? First of all, it's big H from David's diagram. And what do we use the geoid for? Anybody know what we use the geoid for in surveying? Orthometric elevations. All of your benchmarks are based on the geoid. All your benchmarks are based on sea level. So they're based on the geoid. So this is the orthometric height of our distance, our horizontal distance. Yes? And then David also mentioned this morning that we have an ellipsoid height, small h. And that's the elevation of this line based on our datum. And then between the two, we had a value called n, which is commonly known as geoid separation, geoid height, something like that. And I think he also mentioned that n in the continental U.S. is always a negative value. Okay, so based on this, we've got to there. Okay. First thing we have to do is figure out, give me a second here. I've lost my train of thought for a second. We got the 577 at that. Okay. First thing we have to do is figure out this value here. Basically the radius of the Earth. Commonly 2906,000, and you can use that in your calculations, but that's not what they want to see on the LS exam. They want to see the radius of the ellipsoid you're using, okay, which is a little different calculation. The radius of the ellipsoid is based on the radius, its radius sub alpha is approximately, it's an approximation of small r sub 0 from your constants in your zone divided by small k sub 0. There is a big R, or capital R0 and a capital K0. Don't use those values, it doesn't work. Use small r sub 0 and small k sub 0. Basically, this is the radius of the ellipse at the central parallel, and this is the scale factor at the central parallel. I don't understand the whole mathematical relationship, but this is the value they want you to use. And if you get these values from your constant, near your last page, the value for zone 5 ends up being 2900,906.68. Again, you can use this value for our next calculations. You could use 2906,000 for your next calculation. It won't change the end result. But on the LS exam, they want to see this, because this is, quote, the correct way of doing it. Okay, so that represents this distance here, this r sub gamma. Okay, So now we can just solve these similar triangles. And the way you do that is to come up with what's called the ellipsoid reduction factor. Ellipsoid reduction factor. And that is known as R sub E equals this R sub alpha divided by R sub alpha plus N plus H, big H. It ends up being a factor, if you will. It's going to end up being less than 1. We're going down, so it's got to be less than 1 when we apply it to this value here. And again, we calculate this value here. And in the problem, what's n? In the problem, what's the value for n? It's minus 9829. I gave it to you in the problem. If, generally speaking, in California, the value is usually around negative 100 feet. If they give you a problem on the Ellis exam and they don't give you the value of n, the geoid separation, don't assume one. Put in your problem, not given, not assumed, and continue on with your calculations. They got to give you credit as you go along if they forgot to give you a piece of the problem. I don't know how you would handle it on multiple choice.
Call Rick.
Yeah, stop the test and call Rick. And then H simply is the elevation. H then is the elevation. So we're taking this, and then we're dividing it by this. I know you're on the plus n, which is a negative value, plus h, which ends up giving us then a scale factor to get from here to here. And if you do the math, normally in my classes I make the people do the math, but I don't think we have time here. You get 9999 5107. 9999 5107. If you do the math here and you get 0.537, something's wrong. It's always going to be probably 3 nines, maybe 4, and some numbers. Take it out to 8 decimal places. That's common practice. But it's going to be something very, very close to 1. If you got 1.0004893, what would that tell you? You went the wrong way. You're actually now going from here and you're going this way. Yeah, so think about it. Before you check your math that you did the math rack, make sure the math makes sense. If we're going to a shorter distance, then that's got to be less than 1. Yeah.
Would this be then, so it would be the combined factor?
No, we're not to combine. This is what's called the ellipsoid reduction factor. This gets us from the elevation we took our measurement to to sea level, basically. To our geodetic, no, not to ground, from ground, to our math model. Good. And if you apply that to that, okay, and remember, what we're actually calculating, since we have a straight line here, what we're really calculating is this chord distance here, which is called the long chord, or simply L sub C, is going to equal R sub E, our reduction factor, times D, which is our length here. And if you do the math, I think you get 8232.174 feet. And you guys all know if the final answer has to be in hundredths, you always carry your calculations out to thousands to avoid round-off errors. If your answer is going to be, and you're not going to carry it in your calculator, you always carry out one more decimal place. So now we've got this distance. Question at this point? But what's the true geodetic distance? is the true geodetic distance measured along the chord. The true geodetic distance, they call it S, or whatever Greek letter that is actually measured along the datum. It's measured along the spherical surface of the datum. And there is in your handouts a formula you can use to make the conversion. It's 1/10 in 19 miles. The Earth is so big that the chord distance versus the arc distance is almost no change. It's 1/10 in about 19 miles. So, for all the problems probably you're ever going to be involved in on the LS exam, though I can think of one where it would apply, you don't have to worry about the second term here, or the conversion from the long chord to the geodetic. So in this case, LC equals this, S equals LC, which equals the 8232.174, and once again, S represents the geodetic distance. So now we've gotten to sea level, mathematical sea level based on our datum. On this particular problem, it's not that close to the center of the Earth, but our grid plane is down there. Okay? And what we have to do now is determine what's called the scale factor. You've got ellipsoid reduction factor, you have scale factor, and a lot of you may have heard of combination factor. We'll come back to combination factor in a minute. Scale factor, we know the mathematical relationship from here to here. And it's given to us again back in your projection tables. It's given to you in the projection tables. If you go to the far column on the right, you will see scale factor. The far column on the right, you will see scale factor for every even minute of latitude within this zone. Okay, so we know that the latitude, wait a minute, I got to think about this for a second. Sorry, hang on just 1 second again, I apologize. What did I do with my math? There we are, I get to there. So we got 174, right? Okay. Okay, we are okay. So, we know that Bernardino is somewhere between 34:17 degrees north latitude and 34:18 degrees north latitude. That's given to you as part of the problem, right? Okay, so if you look at the projection tables, K, small k, which is your scale factor, for 34 degrees 17 minutes equals 0.123495523. Can everybody find that number? And then for the small k for 34 degrees 18 minutes, 0.9999 5292. Okay? Okay. Unfortunately, in the projection tables, they don't give you a tabular difference to figure this one out. You just got to do a simple proportion. Okay? So, the simple proportion, the difference between these two, if you will, is 0.0000231. If I were to subtract these, I get 0.12345. 231. Okay, let's just work with the 231. Forget these zeros for a minute. You can do it if you want to. And this is the amount of change in your scale factor over what dimension? 1 minute or 60 seconds. Okay? And X, we need to know how much it's going to change at 42.54378 seconds, which is the number of seconds in our point, in Point Bernardino. And this is the number of seconds in the latitude of Bernardino, right? And if you go through and do all the math, x ends up equaling 164. About two-thirds, yeah, it makes sense, which actually equals 0.12345,164. That is the amount of change in the scale factor from 1 minute to the next minute, from 3417 to 3418. Make sense? Got everybody lost? Clear as mud? Okay, now what do I do with this value? Since these values from 3418 to 3417, since this is smaller, we got to subtract, right? We have to subtract it from, actually, I got to think about it. What did I do? Yeah, I subtracted it from this value. Since we did the calculate, got to subtract it from this. And your scale factor then, K for Bernardino, equals 0.12349, 5359. And that will then take us from our geodetic down to our grid distance. So now we're going to take our distance of our geodetic distance, which is 8232.174 times 0.99995,359, and that's going to equal 8231.792 feet, which represents our grid length. They call it L sub grid. Clever. Okay, so now you have grid coordinates. You have a grid azimuth from Bernardino to Riverside, and you have a grid distance from Bernardino to Riverside. You get out your HP, you put it all in there, and you run through your traverse pack, and you end up with coordinates. If you want to run through this problem at home or whatever, you end up with coordinates for Riverside of north 1930, 589.99 feet, that's a 9, and an easting of 6,900, 621.13 feet. Pardon me? 13. Okay. A couple things I want to go through just to confuse you a little bit more before we get out of here. And this is dealing with scale factor. Let's say, now our line happened to be pretty close to an east-west direction. Our azimuth was relatively close to an east-west direction. So the scale factor stays the same. Scale factor changes as you go north and south in the zone. But what happens if you've got a geodetic distance that is going like 45 degrees north, or an azimuth of 45, and the distance is like 77,000 feet? Do you calculate the scale factor here for the entire line? You'd have to scale, you have to figure out what the scale factor is at about midpoint. And how can you do that easily, relatively easily, and come up with a value you can use? It won't be exact value, but it'll be close. Okay, we know our latitude here, correct? We know a direction. Let's say the azimuth's 45 degrees and the geodetic distance is 77,000 feet. Don't have to have exactly grid azimuth or geodetic. We're not doing anything perfect right here. We're just trying to get an approximation. But if you know this is 77,000 and you know the azimuth, you could calculate the latitude, as in latitude and departures, or the difference in northing between this point and this point, correct? If you divided that by 2, you'd end up with the difference in northing between your midpoint of this line. Make sense so far? So now you have a distance from here to here, the difference in northing, whatever it is, in feet. And you need to know what value here to get your scale factor. Scale factor is based on latitude, right? So we need to figure out what the latitude is at the midpoint. What can you use to convert that to latitude? Or the difference in latitude between the two? How about the tabular difference? How about the tabular difference? 101 point whatever. If we take this and divide it by 101.08 or whatever it was, what would that represent? That would represent the difference in latitude between the 2 points, right? Then you could simply, in this case, if you're going north, you've got to subtract it from this, right? No, add it. Sorry, you got to add it. You're going north. You got to add it to this, and you would have the approximate latitude of the midpoint of the line. And then you could develop your scale factor, K, based on this value rather than this part, and get a better result. Okay? Make sense? Combination factor. Some of you may know that value. Combination factor is simply the ellipsoid reduction factor times the scale factor. Combination factor is simply the ellipsoid reduction factor, the elevation factor, times the scale factor. And if you're working on a job of limited extent, where you're not going real far north and south and the elevation is generally the same, you can calculate a combination factor from that job and go straight from ground elevation or ground distance to grid distance, or vice versa. If the job is designed in grid, Caltrans, you can bring it up to ground. And then you're staking at ground. Does that make sense? So combination factor is just the two together. Any other questions on this stuff? I had the error part of that. That would kill you probably if we went into that. Your heads would explode. So I'm going to stop now. I'm going to answer questions. We went really fast through this. Like I said, I usually get 6 hours, and you guys get to do the math, and it's a little more sensible that way. We had about 2.5 hours, a little less today, and I went through this really fast. You can contact me if you have any questions about this problem. If you want me to send you my answer sheet, which is kind of a mess, but I'll be happy to send it to you. J. Evans at Somas, that's with a P, the P is silent, somas.com. You know,
Are you uppercase? Or is that just...
Doesn't make any difference. J. Evans at somas.com. We got 20 minutes to kill, but I don't want your heads to explode either. So it might be okay to get out of here. Are we going to get in trouble?
Before you go.
Yeah.
Before